All right, this is Note-Taking Guide 7.2. This is for mathematical decision making for life. And today we're going to talk about something called graph theory. So graph theory, when we talk about it, we actually usually start talking about a mathematician whose name was Leonhard Euler. His name is spelt this way. It doesn't really look like Euler, but that's how you say it. He lived in a Prussian town called Konigsberg at the Baltic Sea, and it had this river running through the town and had a ton of bridges to go over the river, 7 actually in this town. And he started to wonder if he could go over each bridge in the town only one time and hit every bridge in the town. So, you can't repeat bridges, and you can't, you have to make sure that you hit all of the bridges. So I'm just going to try it a few times and see. So this was the actual city up here, and he made it into what we would call the graph of the city by just really taking the bridges and the land masses and having us look at those instead of all of the details of the city. So let's just say we start here at this bridge, and we just want to go over every bridge that we can in the city. So look at that, you guys. We did really quite good, but we got to go back over this bridge to get to that one, so that didn't work. So let's try it again. Let's maybe start on this one and see if we can get it first, and then maybe here. We're still stuck with that one bridge that we didn't go over. So what Leonhard Euler did was he studied this, and he found some rules that go along with graphs and the theories of graph of how whether or not we can trace over those bridges or over those points more than one time, or if we can or can't. And so what we're going to do is today we're going to kind of just take a look at some of these graphs and see if we can find paths. Then I'm going to teach you the rule that Euler actually came up with to determine whether or not you can find a path. Because sometimes we're like looking for a path, and we're like, I don't even know if there is one. Well, I can tell you how to find out whether or not there is one, so you don't have to keep trying over and over and over again. So let's take a look at this set of bridges right here on this landmass over here. And let's see if we can go over every bridge exactly one time and only one time to get every bridge covered. So I think I'm going to start here, and let's come this way and see what happens. And that didn't work, so I'm going to try that again. Maybe I'm going to go like this time. Oh, there we go. I just did that, you guys. Did you see how I got over every bridge one time, exactly one time? So my answer on this one is yes, I can do that. So here, let's give this one a couple of tries and see what happens. So maybe we start here and come this way. I don't know if we should go. That didn't work. I already messed up because I'm going to get stuck no matter where I go. I can see that happening. Maybe if I start in the middle, come out, go around, back to the middle. I'm stuck if I go that way, and I'm going to get stuck if I come this way because I can't go back. So I'm going to guess on this one, you guys. I don't think this one's going to have a way to make that happen. But again, right now we're just guessing and checking. We're not really sure. So let's check this next one and see. Maybe I go this way, back around, and then I'm stuck. So that didn't really work. That wasn't very successful for me. Let's see. Maybe I can come here and go. So that was pretty good. I got all except for one bridge there, but that one didn't work either. I feel like no matter where I'm starting on this one, I'm kind of getting stuck because I can't get there. So I'm going to guess no on this one also. Now let's look at this last one right here and see if I can figure this out. Maybe I'll start here. And I think I did it. I got around every part with only touching the edges once. So yes on that one. Okay. So that's kind of annoying to just kind of keep guessing and checking and guessing and checking. So it would be nice if we could come up with a way that would make that easier for us to figure that out. So every day we're surrounded by countless connections, networks, roads and roads and train tracks, phone lines and internet, electronic circuits, and even molecular bonds. There are also social networks between friends and families. In mathematics, these networks are called graphs, and here's a couple examples of what they could look like. The vertex points are represented by points, and that's what it says. A graph is a collection of vertex points that are connected by what we call edges. So here's an edge, a line that connects two vertex points, and then those vertex points are the solid dots there. Okay, so Leonard Euler observed that some graphs can be drawn so that you can trace each edge only once. Some even have many possible paths, while others you can't trace at all. Which graphs can be drawn without lifting the pencil off the paper and without drawing any line twice? Try the following examples and see whether or not you can find a pattern. So you guys, knowing that we just talked about edges and knowing that we just talked about vertex points, maybe we should see if we can figure out one that works and take a look at it and see if we can find a pattern in what we're doing here. So what do you think? Are we going to be able to trace this one and make it happen? So let's see let's just pick a spot to start and see if we can make it work. I think I'll start right here. Oh, okay, that was a nice guess, or was it a guess? I don't know. That one actually did work. So before we move on any further, let's just kind of count. I want you to see how many vertex points we had. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertex points. Now, I don't know if that is going to help me figure out anything or not, but that's 12 vertex points. And then let's just kind of look at the vertex points and let's see if we can find anything special about them. So let's count the edges that come into each vertex point. So this edge has 2 lines coming into it. This vertex point has 2 edges coming into it. This vertex point has 2 edges coming into it. This has 4 edges coming into it. This has 4 edges coming into it. 2, 2, 4, 4, 2, 2, and 2. So, just kind of looking at that and seeing how that's working. Make sure I counted those all right. All right, so let's just go to the next one now and let's see whether or not we can figure out how to do the next one. All right, let's look at the next one and see if we can trace it. So we're going to try and get over every edge only one time and see what happens here. So I think I'm gonna try zigzag first. And I'm stuck there, I can't go any further. So let's try something different. That did not work either. No, that doesn't work either. So I'm gonna guess no on this one. Okay, and then let's see if we can figure out why. So let's count edges that are coming into each one. So 2 edges come in here, 3 edges come in here, 2 here, 3 here, 2 here, 3 here, 4 here, 2 here, and 3 here. So looking at the edges that come into our vertex points, do you notice a difference between this first problem and the second problem? So, or notice a similarity? I'm not sure either, but let's go on and let's keep going with the third one here. So let's see if we can trace this one with catching only every edge one time. Oh, I did that one pretty easily actually. That worked really nice, you guys. That one is an answer of yes for sure. So let's take a look at its vertex points and let's see how many edges come into each vertex point. So here's 2, 2, 3, 2, 2, 2, 4, 2, 3, 4, 4, 2, 2. All right. Okay, so let's just go through these other ones right here and figure them out, and then let's just go see if we can figure out the rule. Now that we have some examples that have those written for us, maybe we can see the rule in just a minute. So let's see whether or not we think that we can trace this one. So let's start and see. So that did not work. Maybe I'll go up this way. Oh, that worked. That was nice. So that one's a yes. Okay, how about this one? That didn't work. Let's try it again. Oh, that worked. That one's a yes too. And then this one. Oh, that got me into a corner already. That didn't work. I'm stuck without one. So I'm going to guess this one is a no. Okay. Let's go on and see if we can figure out the rule. Before we do, though, let's talk about a couple more things, okay? We're going to talk about the order of a graph. The order of a graph is how many vertices it has. So this has 1, 2, 3, 4, 5 vertices. So this order is 5. And then this one has 1, 2, 3, 4, 5, 6, 7, 8 vertices. So its order is 8. The other thing that we want to know about a vertex point is something called its degree. And its degree of a vertex point is the number of edges that it has coming into the graph at that vertex point. So for instance, if we're looking at this vertex point, it has 1, 2, 3 edges coming in. So its degree is 3. If we look at that next example, if this is the vertex point we're looking at, it has 1, 2, 3, 4, 5, 6 edges coming in, so its degree is 6. So let's see if we can figure out how this is going to help us. Any route around a graph that visits every edge once is called an Euler path. We can tell which graphs have an Euler path by counting how many vertices have an odd degree. So just like we were counting how many of those edges came into each vertice before, we're going to do it now. So this has 2 edges coming in. This has 4 edges coming in, 3 edges coming in, 3 edges coming in, 4, and 4. So that's how we count the degree of each vertex. We're going to do the same thing here. 2 edges coming in, 3 edges coming in, 2 edges coming in, 3 edges coming in, 4 edges coming in, 3 edges coming in, 2, 3, and 2. So how is that going to help us? Well, let's go and let's read what Euler's rule is. He says, as you visit and exit each vertex, edges are always added in pairs. The only exceptions are the vertices where we start and where we finish our path. If we start and end at 2 different vertices, only these 2 will have an odd number of edges. If we start and finish at the same vertex, then all of the edges are even. This makes it possible to determine whether graphs can be drawn just by looking at them, and even where we're told to start and end. An Euler path is possible if and only if there are at most 2 vertices with an odd degree. So let's go back and look at some of those ones that I had us originally writing things on. Do you see how this one had only even degrees? Do you see how this one had exactly, I shouldn't say exactly, it had more than 2 odd degrees to it, so we knew that we couldn't trace that one. This one had exactly 2 odd degrees on it, which means I knew I could trace it. So when we're looking at whether or not we can trace a path, we're looking to see if there's at most 2 vertices with an odd degree. So again, back at these ones, we didn't trace these ones, but let's just look and see if we can trace these ones. So let's look at this for a minute. I have 1 odd degree here and 1 odd degree here, which means yes, I should be able to trace this. On this one, I have an odd degree here, 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 and here. So that's going to tell me no, I am not going to be able to trace this. Okay, so again, that's what he says. Euler says that you have to have at most 2 odd degrees. Okay, so let's go back and look at that original example, that Bridges of Königsberg, and see whether or not we think that we can actually trace it. So this is a graph representation of the city, another way to write it. And if you notice right there, I didn't trace it right again, but let's look and see if we can. So written, here's a graph representation of the graph over here. So let's take a look at our vertices. This has 3 edges coming into it. This has 5 edges coming into it, 3 edges coming into it, and 3 edges coming into it. So what do you think, you guys? Would we be able to cross all of those bridges only one time in that city? The answer is no. We cannot find a path that it will work for. So that is Euler's theory. Actually, we did a lot of math here today that was kind of just, the assignment's going to be much easier than this because now you know how to count those vertices to see whether or not you can actually trace them. Most of the time today on the assignment, we don't make you find the path. We just ask you whether or not it can have a path. So you're looking for only 2 odd degrees. The rest need to be even. Or no odd degrees at all would also work. Okay? All right, thanks for watching, you guys. Good luck with your homework.